All right, let's get right into it. Today, I'm putting on my master automotive technician hat to talk about something that happens on the side of the road literally thousands of times a day, yet it is wildly misunderstood. We're going to completely shatter a massive myth today, the idea that a simple roadside jump start is harmless just as long as the car eventually fires up. The truth? A modern car isn't just an engine anymore. It's essentially a highly sensitive network of computers on wheels. And when you clamp on those jumper cables, you're executing a really high-risk electrical procedure that can silently fry those computers.
Okay, grab your clipboards, let's dive into this. Here is our roadmap. 1. Anatomy of a power surge. 2. How car computers fail. 3. The master diagnostic workflow. 4. The true cost of damage. And finally, 5. The bulletproof jumpstart.
Starting off with Part 1, Anatomy of a Power Surge. We're moving from the macro level of thick battery cables right down to the micro level of sensitive circuits to understand the sheer electrical violence of jumper cables.
So take a look at this massive disparity. Your engine control unit, or ECU, comfortably operates between 9 and 14.5 volts. But internally, the actual logic circuits are running on extremely delicate 3.3 volt or 5 volt regulators. Now, during a botched jump start, your vehicle's electrical system can be slammed with transient voltage spikes hitting anywhere from 40 to 120 volts. Think about that. For a tiny microchip designed to sip just 5 volts, getting hit with 120 volts is an absolutely catastrophic, violent event.
Let's walk through the exact chronological timeline of a bad jump start. Basically the crime scene. First, the very second those cables connect, boom, there's an instantaneous equalization surge of 200 to 400 amps between the batteries. Second, the guy in the donor car usually revs his engine, right? Thinking he's helping. He's not. It just pushes their alternator output to dangerous voltage peaks well above 15 volts. But Phase 3 is the real killer. If you pull those cables off while the engines are running and under load, it creates a sudden interruption of current flow. This causes a massive microsecond inductive kickback, also known as back EMF, that shoots through the entire electrical system at up to 120 volts.
Now you might be wondering, don't cars have built-in protection against this? Well, yeah, they do. Circuit boards use components like transient voltage suppression or TVS diodes, which are specifically designed to clamp these spikes at around 24 to 36 volts to protect the ECU. But here's the catch. These components only have a finite energy rating, measured in joules. So a massive 120-volt spike, that can instantly overwhelm them. Or, and this is super common, repeated minor abuses degrade them over time until they just fail open, leaving your ECU completely stripped of its defenses. Moving into Part 2, How Car Computers Fail. Let's look at the invisible casualties inside your vehicle's brain, especially the engine and transmission control modules which face the highest risks.
So the crucial point here is something called latent degradation. A voltage spike might not instantly vaporize a microchip. Instead, it severely stresses and weakens the semiconductor junction. It's like a hairline fracture. Over the next few weeks, normal engine heat and everyday vibration just kind of finish the job, causing that weakened junction to fail completely. So if you notice erratic dashboard lights or transmission hesitations, say a week after a jump start, well, you're experiencing this invisible ticking time bomb going off.
When that hidden damage finally shows up, it's very often flash memory corruption. A surge happening during a read-write cycle will absolutely corrupt calibration maps. I actually had a customer recently who replaced 3 oxygen sensors and a mass airflow sensor, just firing the parts cannon at the poor car, when my diagnostic check revealed the true culprit was corrupted ECU data from a jump start a month prior. You'll also see voltage regulators failing, taking down the 5-volt internal logic, or even worse, CAN bus transceivers taking massive damage, which literally pulls the whole communication network offline.
All right, Part 3, the master diagnostic workflow. Let's isolate the damage like a professional, without the guesswork. Here is our professional diagnostic foundation. Step 1, we run a full system scan with a bidirectional OBD2 tool to hunt for ghost codes. We're specifically looking for U codes, like U0100, which tells us there's a complete loss of communication on the network. Step 2 is a physical CAN bus integrity check. Step 3, we verify the supply voltage and grounds to the ECU specifically under a cranking load, because blown fuses can partially disable a module. And finally, we request live data streams from those modules. If a module says it's there but totally fails to stream live data, its internal processor core is probably fried. I want to pause on Step 2 for just a second. 60 ohms. That right there is the magic number. If you disconnect the battery and measure the resistance between can high and can low at the diagnostic port, you should see exactly 60 ohms. That comes from 220 ohm terminating resistors running in parallel. If that number deviates significantly, it tells us immediately that a damaged, shorted CAN bus transceiver in one of the modules is actively loading down the network. From there, a tech can safely test for parasitic drain using an amp clamp, making sure we don't accidentally wake up the modules and skew our data while we hunt down that short.
Another totally pro-level diagnostic trick involves looking at alternating current, or AC ripple voltage. Normal alternator ripple is tiny. We're talking less than 50 millivolts AC. But if a bad jumpstart caused diode failure in the charging system, you're going to see an abnormal ripple of 200 millivolts up to 2 full volts of AC. Testing for this is just a fantastic early warning sign to catch failing diodes way before they cause erratic module behavior across the car.
And this brilliantly illustrates our final diagnostic step, a forensic visual inspection of the board itself. If we suspect a dead module, we pull the board out and put it right under magnification. We are hunting for slight discoloration or hairline cracks on those TVS diodes we talked about earlier. We're searching for microscopic pinhole burn marks on MOSFETs, burnt IC processors, and obvious thermal stress on the printed circuit board traces. It is literally electronic CSI.
Part 4, the true cost of damage, or why diagnostic fees are your absolute best friend.
Look, if you get lucky and it's just flash memory corruption, reprogramming the ECU might only run you $100 to $400. If you have to actually replace a new OEM engine control unit, now you're looking at $500 to over $2,500. But here's the absolute worst-case scenario. A spike travels through the CAN network and blows out the transceivers on the transmission control module, the ABS module, and the body control module all at the exact same time. You are now staring down a $3,000 to $10,000 repair bill. Suddenly, a $150 professional diagnostic fee to pinpoint the exact failure seems like an absolute bargain compared to blindly firing expensive parts at a dead network.
Which brings us to Part 5, the bulletproof jumpstart. How to empower yourself and prevent the surge before it even happens. If you absolutely must use traditional cables, this is the only correct order. Step 1, red to the dead positive. Step 2, red to the donor positive. Step 3, black to the donor negative. And Step 4, this is absolutely crucial, black to a bare metal chassis ground on the dead vehicle. And remember what we said earlier, never ever remove these cables while the engines are revved above idle to avoid that inductive spike.
So why is that last step so critical? Well, chassis grounding forces the electrical current to travel through the vehicle's metal framework. This adds a slight amount of natural resistance, which physically buffers and slows down that massive electrical surge. Plus, it keeps the final connection spark far, far away from the potentially explosive gases hanging around near the dead battery. It is, without a doubt, the absolute safest method for modern electrical systems.
The next big secret is patience. Seriously, once connected, do not crank the engine immediately. Just wait 3 to 5 minutes. This allows the electrical potentials to equalize, letting the dead battery absorb a nice surface charge. That little bit of waiting prevents catastrophic voltage drops and dangerous load dumps when you finally turn the key.
But honestly, if you ask any professional technician, they will tell you to just skip jumper cables entirely. We use lithium jump packs. These devices are absolute game changers. They feature regulated current output, which automatically limits those dangerous voltage spikes. They have built-in microcontrollers that prevent reverse polarity. So, if you accidentally hook them up backward, nothing happens. But most importantly, they completely remove the unpredictable variable of a revving donor vehicle's alternator from the equation entirely.
So I'll leave you with this final thought. A modern vehicle is no longer just a mechanical machine. It's an incredibly complex network of highly sensitive computers. If a rushed, 5-minute jump start can cause $10,000 in invisible, latent damage, is relying on an old set of jumper cables really worth the risk to your vehicle's brain? It might just be time to upgrade your roadside emergency kit.